So essentially what we want to try to describe is a structure like so. Now this structure here is sort of what we want to understand from a mathematical point of view. You can see that a few things jump out at you immediately. It looks to be at least somewhat fibrated, broken up into these white strands. So we'd call that fibrated. Along the meridians, if these are the meridians, these white strands are the meridians, we can clearly see that it's some sort of partition of if we think of it as a surface, it's a partition of that surface into a discrete, or in the picture it's discrete, but it's really an infinite amount of those packed together. So essentially, we would like to have a better understanding of this object. Another thing that jumps out is the singularities. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 cone-like singularities of this, I'll call it a manifold. But we're not really sure what it is initially, but like I said, we would like to understand it a little bit better, more deeply, where it comes from, how it's related to other mathematical objects. So we're going to explore this from pretty much a geometrical point of view. There could be other ways of thinking about it, but I'd like to explore it at least geometrically to begin with. Another thing to note is these loops. These, initially, you might think of them as non-contractible loops, or there's a term called systole in geometry. So basically, it's like if you think of like a rubber band shrinking onto this loop, it sort of cinches around that and can't be tightened further, which might be a helpful way to think about it. So we'll go to the paper and write some things down. So let's look at it one more time. We have that object we're trying to describe. Okay, so we'll start with geometrical viewpoint. Think of this as the base space. And we'll draw some curves. Okay, so we have some curves, and we'll call this, let's say, theta 1, 1. Just by the notation, you can kind of see that it might be suggesting that I am describing a semi-Riemannian geometry where 1 plus 1 is one space dimension, one time dimension. So time will sort of act like this, and space will act like this. Okay, so these essentially are our killing flow lines, which preserve metric G. By the way, this is 0 to 1. This is the unit square, essentially, that we're looking at. And you might say, what is going on here? What is G? What is this manifold? What is this base manifold in the unit square? Well, it comes from basically it's basically a Minkowski space in some sort of strange coordinates related to light cone coordinates and the light cone gauge, if you're familiar with string theory. Essentially, if we view this as a particular Cauchy foliation of, I'll call it R11, H. This would be Minkowski space and sort of light cone coordinates. We have this, where these are our rectangular hyperbola. The killing field would act somewhat like that, where the arrows are just used to describe the flow direction. So right, we have the flow and voila. So what is this map though? Well, it's simply the exponential map. So if we think of this as one component here, this would be the past light cone, right? Future light cone. L plus, L minus, and we get this sort of shape here. Sort of light cone object. And we're gonna think of this as being mapped to here. So what we do is we sort of push this with the exponential map up to the unit square. And I'll just draw a better picture. So essentially we're gonna draw the past light cone L minus in Minkowski space. So that's the past cone. This is L minus, a local picture. I guess not really local, but it's L minus. And then we're gonna use exponential to map these curves. Essentially, it's a diffeomorphism acting on this component of the manifold. And this just becomes under f of xy equals e to the x, e to the y. We get simply this. We simply get this object. Now we can, it's the same as, this is the same as that. Essentially we get zeta 1, 1, g, x 0, 1, phi 0, 1. And like these were our killing flow lines where we have Lorentz transformations driving the infinitesimal flow. Then we have, these would be, if you flow sort of along these curves, you get the same analogous Lorentz transformations. Okay, so that's all well and good. We have the initial setup. With the initial setup here, so you might ask, what are the equations for these curves? Well, they're simply, we simply map the hyperbola to these, and the x mapping. You can simply, as an exercise, you can figure out that it would be, let's say, simply be those for x and 0 to 1, yes, and for s and 0 to infinity. So there we have that. So now we have the equations, and s is a parameter, by the way. It's sort of like a time parameter. So essentially we want to take the next step here. So you can sort of try to build up from this to get that by viewing this as one component and viewing each of these guys. So there's like 1, 2, 3, 4 sort of like zonoids, sphere-like football, American football style shape zonoids. You can view them as like those 4 components intersecting. And we'd like to view each of these components separately as a section lifted up onto that. So it's essentially a section of a fiber bundle or a foliation. So a section would just be sigma. Section. So we're going to lift the manifold. So we'll call this essentially we'll call this the foliation, since since the union of basically since the union of S and we'll call S and S phi S equals essentially this this joint union of all the leaves. The union of all the leaves essentially generates the entire manifold. Or basically the entire manifold can be broken up into one-dimensional pieces. This guy, these one-dimensional pieces that together the union is the manifold. Zeta 1 1 with metric G. Oh, I haven't even said the metric. Right, so the metric G, well, let's cross that out for a second. The metric G, so we have zeta 1 1 G, where G is defined to be dx dy over xy. And that you might recognize that as basically an image of, it's basically a Minkowski space in different coordinates, just like log or exponential coordinates, and with the like cone gauge. So it's basically taking that basically light cone coordinate style Minkowski and shooting it upward into exponential space. So we'll just, for lack of better notation, it equals the manifold. Okay, so now, so essentially what we're doing is we're taking this, and you can sort of see that one of those components might project directly onto it. So those white fibers could project directly onto this manifold. That's essentially what you might expect, or you might try to, in the efforts to understand this guy right here. So now essentially we have the basic setup. We can draw a little picture here. So this guy's going to take place in the cube. So we'll lift the cube to the cube picture. Okay, so we'll call this. So these are going to be pasted on the boundary of the boundary. So we'll have a flat. Basically, here's the picture. Here's the picture right there. So this guy is being pasted on there. There's that. Right. And it's going to be pasted on all these different, so that we have the boundary of this object is flat Minkowski space. So we know that the boundary of this, essentially it's a conformal manifold. And if we think about what this is, right? This is a cylinder. This is a cylinder, right? And it's sort of, if we think about that as ADS, anti-de Sitter, this would be a hyperbolic slice. See ADS. That'd be ADS, right? The boundary is our conformal boundary, and this has negative curvature, by the way. I'm sorry, negative cosmological constant, and this is basically H2 Cartesian product with R, the real line. Let's say essentially it's hyperbolic space. Let's say H2 cross R. This is just, topological for now. I'm not going to get into major details with this. So if we think of that as H2R, right, this is H2, the hyperbolic plane, Poincare plane, and this is, I guess, R. Then we will have ADS, basically a model of ADS. You can sort of see that if I were to not project, but to compactify this guy. So basically blow down the caps. We'll get a geodesic compactification. These straight lines of the geodesics are running vertically. Compactify them all to a point. We're gonna get basically this guy. All right, it's just the geodesic compactification of the cylinder, which would be that. I'll denote this as, I'll call that M3. I will denote this as MG3, denoting that is the geodesic compactification of these panels, of the well chambers, and so on and so forth. So it's basically, we can add a little bit more detail here, right? Add a little bit of more hyperbolic detail. So these are hyperbolic panels there, hyperbolic slices. And I mean, some people like some physicists, like I saw a paper by Sean Carroll, and this other, she's Italian, I forget her name, but they did a paper about these being brains, D-brains. The singularities are basically D-brains. But this is getting more into physics now. I mean, it is related, I think, but I'm not sure how related it is yet. So these are D-brains. And essentially that's it, you know. So we want to copy. So if we think of this guy as sitting in here, sort of embedded in there, sort of embedded, so it's going to sit above, right? It's going to sort of sit above that guy. So this picture's going to get really confusing. Essentially like that. It's going to sit above. And then projecting it down will give this zeta 1,1 object. And in fact, one interesting thing I think this is interesting is when we indeed, so if we were to highlight like that when appropriately positioned in space, like this is gonna project down, right? And what we're gonna get on the base space when we project, it's basically, they're tilted in the cube, so it's a little bit delicate with the projection, but basically you can position it so that these hyperbolic panels actually give something that looks like this. And this is quite interesting. Something that looks like that. These are essentially, if you take hyperbolic space and you were to rotate this curve like that, project it down to a line. Well, you'd get a line, and this is essentially, but it's not a circle really. It's, like I said, it's hyperbolic, so it's a two-manifold. So it's essentially a compactification of this H2. It's essentially a compactification. Let's say, I'm a physicist like string theorists do like these compactifications of dimensions. Could be on the right track, but it would be basically a compactification of this H2 to this, which happens to be geodesics. Well, not happens to be, it was specifically prescribed to line up with the geodesics on here. And these are in fact geodesics, right? Because if we complete the picture here, we get the full geodesics, which look awfully like, they look awfully like this. However, they are orthogonal to that zeta 1, 1. So these are the killing orbits, the orthogonal geodesics along with the killing orbits. This is zeta 1, 1, G. X 0, 1, phi 0, 1. So essentially this, we shoot the geodesics like that, and the killing flow goes like that, or like that. So it's like that. They're orthogonal. Transversal orthogonal. So I think that's all for now. Sort of don't know what else. No page. So we have that. Let's take a look at that. Look back at there. So, what else can we say? Remember, the goal is to try to describe that to the best of our ability. Yeah, so I think this is more so like, I don't know, conjecture or possibly, not rigorously tested yet, but we'll try to at least describe some more thoughts on this. So let's begin with, I guess, more so for the physics part of it. One idea I have is that these are light-like singularities of an induced metric. So if we take this as like sitting in Minkowski space, not sure which, I guess like Cone gauge. Think of that. I mean, think of like this sitting embedded in that. Then the induced metric onto this would emit singularities. I can refer you to a paper. It's called. What's it called? It's by A. Honda, Japanese mathematician or physicist. A. Honda, and the paper is called Isometric Deformations of Mixed Type Surfaces, I believe, and Minkowski and Lorentz-Minkowski space. I might have missed a couple of words, but it's basically, You'll find it if you search that. Why is that blurry? Okay, so we have that. Okay, so I'm not sure why that's blurry. Anyway, I'll probably end the video soon, but his theorem A basically describes, it's basically a uniqueness theorem, and he does a sort of similar construction. So he basically views this as, he would say, is like these rubber band curves would be like singularities of the induced metric, and yeah, basically like that's what he discusses in his main theorem of that paper. So I think that is all. See you in the next video.